Decai. In this talk, we present our work recovering fine details for real implicit surface reconstruction. 3D reconstruction from calibrated multi-view images is a long-standing challenge in computer vision. Classical pipelines involve several steps, including depth map estimation using multi-view stereo, fusion into global space, and surface extraction. On the other side, implicit real representation directly optimized MLPs for scene geometry and appearance without 3D supervision. Surface rendering-based implicit real reconstruction methods sample only the surface intersection points along each ray for optimization and struggle with reconstructing complex objects. Thus, they usually require additional supervision such as object masks, depth maps, and point clouds. In contrast, volume rendering-based methods approximate the surface point using alpha composition without prior knowledge. However, accurately recovering fine detail is still challenging for these approaches. In this work, we present D-NeuS, a volume rendering-based real implicit surface reconstruction method capable to recover fine geometry details, which extend D-NeuS by two additional loss functions called geometry bias loss and feature consistency loss. Assuming the local surface as a plane, which is the first-order approximation of SDF, the ideal SDF value of sampling point is linear along the camera ray. Based on this assumption, D-NeuS derives unbiased weight distribution. However, we argue that the ideal SDF distribution is not guaranteed by the geometry MLP network. Unregularized SDF distribution causes bias between the SDF implicit surface and the volume rendering integral, and thus the inconsistency between the color radiance field and the SDF geometry field. At this point, we propose to regularize the SDF by constraining the geometry bias. Specifically, we penalize the absolute value of the sign distance of the rendered surface point. Guiding geometry reconstruction with multi-view photometry or feature consistency is popular in MVS and implicit real reconstructions. Typically, photoconsistency approaches comparing the photometric distance across image patches require the surface normals to compute homography, while feature consistency methods match only a single pixel between the feature maps, and the high-level deep feature representation is considered more robust against noise. Therefore, similar to MVS-DF, we apply feature consistency to constrain our reconstruction. To find the surface point differentially, we take the advantage of SDF values of sampling points, which are already calculated for volume rendering, and search for the first pair of sampling points changing the sign of SDF from positive to negative, and then approximate the zero-crossing surface point using linear interpolation. Note that similar strategies for ray surface intersection are used in IDR for surface rendering and recently D-NeuS for photometric consistency. In contrast, we apply feature consistency in volume rendering. Here are the quantitative evaluation on D2 dataset. We outperform the state-of-the-art in both geometry reconstruction and rendering quality. Qualitative reconstruction on both DTU and blended MVS datasets also demonstrate that our methods reconstruct high-accuracy surface with fine details. Thank you for your attention. Please refer to our paper and code for more information.